What's up, peers, and welcome to the World Crypto Network, here again from the Understanding Bitcoin Conference in Malta. And today, right here next to me, I have one of the awesome contributors to the Bitcoin Core project, Jonas Nick, a employee from with Blockstream, working there and doing some awesome research, some awesome development. Jonas, how are you doing?
Hello, doing great and enjoying the conference so far. And looking forward to what's next today and tomorrow.
So you showed a bunch of cool stuff here already and did a couple panels and demos and all that. But before we get into all that, so maybe a bit to your background. Why are you in Bitcoin and what are you up to?
Why am I in Bitcoin? I think initially I started looking at Bitcoin because I saw that you could have censorship-resistant money, so you could just transact globally without anyone asking for permission. That was a second very interesting aspect for me, that you could just build software using money and trading. I mean, not necessarily currencies, but goods or digital goods. Without having to ask a bank or PayPal or Visa or MasterCard or whatever to use their APIs. You could just use Bitcoin. Initially, I found that really appealing, and this is why I started contributing to the project.
Cool. And so did you started contributing directly to Bitcoin Core, or and then later, how did you get into Blockstream and kind of what was your initial job there?
I think, to be honest, my initial interest was how can I break these things? Because in some sense, they are also very fragile, right? There could be a single bug in a cryptographic implementation and suddenly everything breaks down. An attacker could create coins out of thin air or spend everybody's coins and so on. So I looked not specifically in Bitcoin, but in a couple of altcoins in the beginning, but I looked into Bitcoin also just to analyze privacy. And I wrote my master's thesis about this topic and analyzing various heuristics. And then afterwards, I joined Blockstream, worked on Liquid a bit in my spare time, and also as part of my job at Blockstream, I was already contributing to libsecp a little bit, the cryptographic library that Bitcoin Core uses. And at Blockstream, I've also I've set up quite a few Bitcoin nodes and was also able to give feedbacks and do some minor commits in Bitcoin Core, but I've mostly been focusing on libsecp.
And I mean, of course, the cryptography side is very important, as you said. If there's one little bug in there, it blows everything up. Right? And it's not like this is like easy 1 + 1 = 2 math, but it's actually complicated, right? And actually, not too many people are like really in-depth familiar. So like anyone contributing is of course very, very valuable because the more people look at it, right, the more secure it is. So did you actually find any critical bugs either in altcoins or in Bitcoin?
So just one thing, mostly the math that we use is relatively straightforward, relatively. I think if you remember maybe groups or something like that from some people have seen it in high school, and that's basically it. At least like some number modulo some other number and how to add and subtract and multiply in this group, that should be sufficient for understanding how signatures work. But the bigger problem is mostly the implementations because I don't know, computing sucks in some sense because there's so many mistakes you can do. So that's a bigger problem. So yeah, I've found a few bugs. Started with Ethereum. They had an initial bug bounty program like before they started, and you could create coins out of nothing, out of thin air. That was fun. And the other one was you could forge signatures. So it was basically broken twice. Yeah, but it was a bug bounty program, so I was paid for it. That was fun. I was
So were you paid in Ether or Bitcoin?
luckily I was paid in Bitcoin. Yeah, but I should say I donated more than half of it. Yeah, I also looked into Monero because that's also interesting. Because like, what if there's a bug, a cryptographic bug, and it can't even be seen somehow that this happened? So that was also an interesting question. Although I think in the bugs so far in Monero, that's not the case. You can always see if it happened or not.
Yes, but I think like exactly what you describe here happened in Zcash, right? They had an inflation bug and no one noticed it other than the devs, right? And they had full insight into that, but the blockchain did not see it. And as far as I know, they didn't disclose it for half a year or so. So that's right. Of course, the trade-off here was perfectly binding and perfectly hiding. And if you don't see anything, well, that's good for privacy, but it also is bad for the audibility of the chain.
Yeah. So luckily in Bitcoin right now, at least you can just add up numbers and see if it sums up to 21 million in the end.
Yeah, awesome. So, okay, well, as we said, right, like signatures, cryptography, that's really your forte. And unfortunately, you're not wearing the shirt today, but yesterday you wore the Schnorr signature shirt. So you're such a cryptography nerd that you even have your clothes in that. So that's always a good sign. So maybe just because we haven't talked too much about Schnorr signature, especially the details in it. So could you give like the quick intro in the cryptography side of Schnorr?
Okay, so right now, in order to do and create signatures, the Bitcoin protocol uses ECDSA signatures, the elliptic curve digital signing algorithm. That's mostly because it was more popular at the time, because it was patented until 2008, I believe, something like that. And Satoshi just used OpenSSL and it didn't have Schnorr. Schnorr signatures are very similar, a little bit more straightforward, and they can be proven secure in a much more meaningful model than ECDSA. This is nice. They also have other interesting properties. One is they have a very simple structure, which means that we can do things like multi-signatures we have multi-signatures in Bitcoin right now. You have the opcode for doing multi-signatures, and in order to do that, you put two public keys, say, on the chain, and then two signatures. And what you can do if you had Schnorr signatures in Bitcoin is both parties could interact with each other, communicate, and create a shared public key, such that they both need to create a partial signature. They can combine the partial signature, and then they have a single signature. So right now in Bitcoin, in order to do that, you need two signatures, two public keys, a special opcode. With Schnorr signatures, you would have one signature and one public key. And just the normal signature verification opcode. So it's shorter, but also a blockchain observer wouldn't see if this is a normal payment or some multi-signature wallet or what this is. So this is one of the things that Schnorr would provide.
Okay, and if I'm correct, that's key aggregation, right? And so is key aggregation only possible for n of n, so for equal amount of keys, like say 2 of 2 or 4 of 4 or whatever? Or is it also possible for m out of n? So let's say 3 out of 5 or 7 out of 11 or something.
So this is also possible. This is mostly called threshold signatures then. And this is possible in a way where you pre-share the keys such that M of n are able to reconstruct the final key. So everyone generates a key, and then you share. Everyone shares their key with everyone else in a way such that M of these n participants can reconstruct the key. So there's a pull request for this in Blockstream's fork of libsecp, where we put all the like more crazy stuff, I should say, right now. It's called libsecp-zkp. This is also where confidential transactions are implemented and a few other things. Maybe I should say that with ECDSA, these things like multi-signatures and threshold signatures are also possible, but they're quite a bit more complex in both the math behind it. You need more assumptions, but also the implementation is more complex, but it's not impossible. I think it's maybe even interesting to look into how to do it. The implementations I've seen so far are not constant time, which is a property that you would want to have for cryptographic implementations, which means that basically the time it takes to sign a message is dependent on your private key. And if you have this property, that means that an attacker in some way, like giving you some messages and measuring the timing or measuring the voltage of your hardware wallet, can try to extract the private key. And because in ECDSA it's more complicated to implement threshold signatures and multi-signatures, it's harder to avoid this kind of side channel.
Okay, very interesting. And so is there, okay, so for multis, or for n of n multi-signatures, there is only one public key then that you put on the blockchain. Is that the same for m of n threshold signatures, that there's only one public key?
Yes, would work in the same way. So in terms of, I said that the participants, they need to interact and communicate with each other. So this whole process, if it's just a multi-signature, the MuSig protocol, then it's 3 rounds, unless you add some more zero-knowledge tricks. But if you do the threshold signature thing, then it's more rounds, because first you need to establish this shared key, and you need to share it, and then you need to make sure that the key is actually shared, and so on. So it's a bit more complicated and might not be feasible in every situation, because you need so much communication during key setup only, though.
Okay, so that would be a lot of communication over whatever channel, right? That can be like maybe could be QR codes or something like SD cards or like SneakerNet, something like that, or of course Tor or other ways to communicate. But it's only for setting up the public key that we then commit to on the blockchain. And what would then be the step for proving the signature, or no, sorry, for doing the signature?
In order to create the signature, you would just use the secret key that you have previously created during the key setup step. Because if everybody shares their secret key with everyone else in a way such that M of n can reconstruct the key, then everyone takes these key shares, computes their new secret key, and this is sufficient. They just use the secret key to sign the message. And magically, due to the linearity of Schnorr, it all works out, and suddenly you have a signature that's valid for the public key. But maybe one note on the interactivity of these protocols. It's because it's multiple rounds, and these multiple rounds, they need some kind of state. So anyone engaging in these protocols needs memory, and they need to store some state somewhere. They need to remember something. Now, the problem is if they are somehow tricked, or due to some implementation bug or whatever, if they use the same state twice. This would be a problem. If they would clone the state or something like this, this would be a problem, a big one, because this can leak the secret key. This would be similar to the problem with nonce reuse in ECDSA and Schnorr. So you could just compute the secret key after seeing a signature. So this is why right now it's, with the current implementations we have, it's probably not recommended to do this on some kind of hardware wallet.
Why specifically not in a hardware wallet? Because not enough memory?
Because hardware wallet needs to shut down, and so let's say if you have it's implemented in a way where if you keep everything in your memory, you're fine, as long as you don't copy the state. But what if you have some kind of persistent storage? So you store your state and then you retrieve it, and then you need to make sure to delete it such that you don't have the state twice, right? So this is a problem if you shut down and you have persistent state. There are some ways to get around this, and or at least reduce this kind of attack surface. But there's one way to actually fix this problem, which would be by using a zero knowledge proof and prove that you derived your nonce in a deterministic way, and this would prevent attacks. But so right now at Blockstream, we're trying to figure out how to exactly do that, because the zero knowledge proofs in general are or they take a lot of computing power to prove, and with small hardware wallets, you don't want to wait minutes for your transaction to be signed. So we try to optimize that and also figure out what exactly the security properties are.
Okay. And one or two steps back, for setting up this threshold signature, you said that they are sending or sharing the secret key.
Yes.
Is it actually the private key, or is it the public key representing that secret key?
This is actually the private key. They're sharing the private key, but in a way such that M of n can reconstruct it.
So let's say there are 3 people, and we want to have a 2 out of 3 threshold signature key, or threshold key and signature. Then Alice, Bob, and Charlie each individually create their own private key.
Yes.
And then they share it with everyone else. Yes. Okay. Can you take over and go like step by step? How exactly would it work?
Okay, so Alice, Bob, and Charlie each have a secret key and a public key. So the first step they do is they aggregate their key together, as in MuSig. Okay?
To create the public key.
Yes, their shared public key. Basically, they just add up their public key. It's a little bit more difficult, but they just add their public key up. That's the intuition behind it. So now, at this point, because the public keys are just added up, it would require everyone to sign, right? But you want 2 of 3. So what Alice does, it divides her key into key shares. So 2 key shares, 1 to Bob and 1 to Charlie. She gives it to Bob and Charlie. Now Bob and Charlie could work together to reconstruct the key. But that's not what's actually happening. They're not reconstructing the key. They're just tweaking their secret key with a key share such that they can sign with a new secret key, and it all magically works out that this is a Schnorr signature in the end for the combined public key.
Oh, okay. Yeah, that is really cool. I get it now a bit more, but could you please go a bit more into what tweaking the private key is?
So tweaking the private key is, I think if I remember correctly, I haven't looked into this pull request for a while, but I think if you receive key shares, you just add them up. I think that's basically it.
So,
And then you can the main scheme behind this is verifiable Shamir secret sharing, or verifiable secret sharing. So secret sharing is for sharing a key, but it also needs to be verifiable in the sense that you need to know that you actually got a valid key share. Because what if Alice gives Bob and Charlie some other random number? They need to be able to detect this, because otherwise they can't work together to create a signature, because they cannot reconstruct Alice's secret key in that case.
okay, okay. So so the private key is just a large random number, right? And then the key share is just half of the large random number, or how do you compute that key share?
So the key share is computed in a specific way. I don't know how much we want to go into detail there, but essentially what you do is let's maybe leave that. It's a bit hard to explain. I would need a whiteboard. So if people are interested in this, the pull request actually has a write-up of exactly how it works. It's you go to the repository secp 256k1-zkp. There's a module directory, and in there is a little markdown file explaining how it works, because it's a little bit more difficult than just adding things up. Yeah, but if you can also look into Wikipedia and Shamir's secret sharing, because it's also very similar to that.
Okay, very nice. So, and now that they have tweaked their private key, Bob and Charlie can do just a regular signature with that new tweaked private key that contains both their original, like, single private key plus the key share from Alice. And then when Bob and Charlie both do a individual signature, and then they combine their individual signatures, then that signature somehow magically can be verified with that public key that both or all three, Alice, Bob, and Charlie, created together in the very first step.
Exactly. I mean, this is what is implemented right now, but we're having ideas of making it a little bit more robust. Because the problem is, what if, let's say, you have a 3 or 4, and everyone is present, everyone wants to sign, but at the start you need to select 3 people. So you select 3 people to do the signature, and they start with the first 2 rounds, and then one party aborts. And then they have to restart the thing without the malicious party. And for that, you need memory and so on and so forth. So it would be nicer if the 4 parties together, everyone could sign. And if somebody would abort, we can just erase the contribution from this participant. So we're thinking about things like that. But yeah, in general, this is what we try to do. We try to make the APIs such that you don't need to think about these things, because it's really annoying if everyone has to implement these kind of failure cases where someone could be malicious and not follow up, and then you need to remember it and ban them and whatnot. So this would be really annoying if everyone would have to implement this.
Yeah, right. And that's why it's so good to have, like, the library and where the cryptographic stuff is all handled, and the application developers just somewhat like trust that this is actually implemented correctly, right? Okay, really nice. But you said that you have to specify the 3 persons who do the signature beforehand. So if, like, Alice, Bob, Charlie, David, do they have to agree initially that it has to be Alice, Bob, and Charlie then doing the signature, or could it be any 3 of the 4?
No, they have to agree in beforehand. But in this particular case, where it's just 4 participants, it's easy, because at most there will be 3 different signatures. So you can run them all at once in parallel. This is not the case, for example, in Liquid, where in Liquid we have right now a threshold signature that we would need of 11 of 15. So the number of signatures we would have to compute in parallel to not have this happen is like 15 choose 11. So this is a pretty big number.
Okay. So, yeah, but in that sense, right, it's different to how ECDSA multisig is implemented in Bitcoin right now, because you just say these are the public keys, and you choose like 2 of the 3, or like 7 of the 11, and it doesn't really matter which 7 it is. It just have to be 7 of these previously committed to public keys. Is there a way of getting it to that, to that function with Schnorr?
No, and you don't want that, because currently I didn't talk about batch verification yet, did I? Okay. So the problem right now with the check multisig operator is, so it takes the public keys and then signatures, right? And then it basically has to check itself. Does this signature actually, is this signature valid for this public key? No, then check it for the next public key. Yes, okay, then check the next signature for the next public key. Is it valid? No, no, yes, no. So this is really annoying, and it's also, it's not very efficient to do it that way. The biggest problem there is you cannot batch verify this. So batch verification is a property of Schnorr that ECDSA doesn't have. So this is a very clear advantage. And what this means is that if you validate many Schnorr signatures at once, you can do that faster than verifying them one by one. So the numbers are in the Schnorr BIP, but if you have like a couple of thousand signatures, I think 2,000, 1,000, something like that, then it's twice as fast to verify them all in one block than verifying them one by one. So in general, when we design the signature specification in Bitcoin, we want to have it such that it's batch verifiable, because it's a pretty big speed up that you can get. Also, for example, for the initial block download. Right, so this is why the check multisig operator actually needs to be reworked in a new script version.
For Schnorr or for ECDSA?
There's no reason for ECDSA in the new script version.
Yeah. Okay. Yeah. Okay. And then maybe just to touch a bit more on batch verification. So let's assume that we have Schnorr in the protocol, and let's assume that there is a Bitcoin block that has presumably all of the signatures being Schnorr. And what we then could do is kind of like batch all these together, and with one computation, with one go, calculate or verify if they're correct or not. And what would happen if one of these signatures is not correct?
Then someone send you an invalid block, and you probably want to ban them or something. Because it's, I mean, you do it for transactions, but if it doesn't, you don't need to find out. I mean, it's true. If you get a bunch of signatures and you batch verify them and it fails, you don't know which signature didn't verify. You don't know which one it was. But in Bitcoin, the cases where this is interesting, it doesn't really matter which one it is. You can just reject the whole thing, like the whole transaction or the whole block.
Yeah, okay, that makes sense. So, and theoretically, if we have several blocks worth with all Schnorr signatures in there, could we batch validate all of them? So then basically, if we have a whole blockchain of Schnorr 6, would it just be one like giant verification of all these signatures with one go?
Yes, you can do that. You get diminishing returns, and also it needs more memory, right? But like for regular personal computers, it shouldn't be so much of an issue.
Yeah, okay, that is really cool. But then maybe how would that work, especially during initial block download? So you would download, let's say, I don't know, like 10 blocks at a time, and then check if like inputs or outputs equals wait, no, inputs are larger than outputs and like all the other consensus rules. But then for the signature validation, it would be all the last 10 blocks, for example, however much memory you have at once.
Yeah, so a block can have, I don't know how many signatures a block have, like 3,000, 4,000, 5,000, something like that. So I think it's much simpler to just for now do batch verification block by block. But in principle, I think this would work. The question is like, how much do you really get from it?
Yeah, okay, really nice. And does there have to be any like any commitment or no, wait, okay, no. Oh, one tackle that from another point of is could we do a key aggregation, for example, of all the keys in the block and put that aggregated key in the block header, for example? And in that way, then we can validate by just validating the one single signature. If that was correct, would that work as well?
So not with key aggregation. Key aggregation aggregates a key such that all the participants can, with some policy, create a signature for it. Maybe you're hinting at signature aggregation.
Yes.
So signature aggregation works similarly than in a little bit similar to key aggregation. It's a technique where if you have multiple signatures from multiple people, different public keys, different signatures, different messages, you can interactively aggregate them while still being in the discrete logarithm settings, so no new cryptographic assumption. So, but the key point here is interactively. So either you do that on your own transactions, so you do it with all your inputs. Usually you have like a few inputs and you can reduce the signatures, the number of signatures from the number of inputs to one. But because it requires interaction, you can't really do it for the whole block unless every one who put a transaction in the block talks to each other. You can do it maybe in some way in coin joins. But so this right now, at least for me, is not really on the roadmap because it's in terms of re-architecturing of the whole flow of Bitcoin Core validation. It's a much bigger step than just having like new outputs, basically, which allow spending with a Schnorr signature.
Okay, very nice. Yeah, so maybe let's talk a bit about how we can use Schnorr and where it is both beneficial for privacy and maybe even the scalability or well efficiency. And you brought up the point of coin joins. So how exactly can we use Schnorr to make coin joins even better?
So the way this would work is just if similar to right now, the CoinJoin transaction is created. Everyone checks that their inputs and outputs are included. Now they want to sign it. So instead of just attaching their signature to it, it's now a interactive protocol. So they first uh, exchange nonces. They receive nonces from everyone. They do a partial signature, and then they can combine the signature into one signature. And one interesting aspect is now that this CoinJoin includes a few or many payments, and everyone paid for part of the signature because there's only one signature. So now the part they are pay, so basically the fees they're paying is smaller than if they would have done the payment by themselves, because then they would have to pay the fees for the whole signature. And in CoinJoin, they only pay for a fraction of a signature. So if there are two parties in the CoinJoin, they only pay for half of the signature, basically. Yeah, so I think this is an interesting incentive to use coin joins in the future.
Yeah, right. That is awesome because we drastically reduce the amount of signatures. Um, it's yeah, as you say, you it's even much less than just the regular one single signature because you only pay, for example, with Wasabi, it would be like one, probably 150th of the signature. So it would be tiny. Um, but I'd like to still point out that the inputs and outputs are still there, right? So these parts are still fully in on the blockchain and still require the full payment of the fee. Um, but maybe just size-wise, what is larger, the signature or the input part?
So the input is a 32-byte hash referring to a transaction plus an index, which is 32 bit, so 4 byte, so 36 byte is the input, and signature right now is about 70 bytes, and with Schnorr, because it's just more encoded a little bit more efficiently, would be 64 bytes. So it is a pretty big part of the input.
Yeah, yeah. Wow, okay, that is awesome. But of course, it has to be interactive, right? And just on an implementation point of view, so let's assume as like that everyone communicates as fast as possible. But still, how long does or would that take with, say, for example, 50 individuals like doing that cooperation? Would it be like a matter of seconds? Would it be a matter of minutes?
I guess that just depends how long you want to wait. um, I think, I mean, you have to try it out, but it should be within seconds because you need like 3 round trips or something. You need to reach everyone. Um, so it should be a matter of seconds unless someone is really slow. But of course, we need to factor in that people should use Tor also. So maybe more on the order I would say maybe tens of seconds than less than 10. But this is just like, I don't really know. 50 is a lot.
Yep. Yeah, 50 is a lot. But I mean, yeah, but I'm thinking like, for example, with Wasabi Wallet, right? There are roughly 70 to 100 inputs in every transaction, probably even more. And there are then roughly again 50 to 100 peers doing that coin join, right? But they are online, right? They have to be online in order to sign anyhow, and they do communicate instantly, basically. But if it's just like, let's say 30 seconds, right? That is still rather fast. And I would not say that it would hinder the workflow or just the user experience of that entire thing. So that's really nice to have this huge scalability on the fee side without really degrading the quality of the user experience. That's awesome.
Yes, this is really awesome. But also, I think people can wait for the coin join because it's they need to wait for the confirmation anyway, and there's a good chance that they just want to open a Lightning channel and then use that to do their regular payments. So this is maybe also an we could now talk a little bit about scriptless scripts if you want, because this is also an interesting topic, I think, which is part of this whole Schnorr signature um, field. So I should point out again, this also works with ECDSA. Okay, but with Schnorr, it's much simpler, and we have implemented in Schnorr for Schnorr in libsecp. The libsecp. I think we've implemented it in for libsecp even. It's not merged, but it's part of the. No, it's in MuSig. Whatever. Because it has to be MuSig. So the way Lightning works right now is that you have these HTLCs to forward payments, and these HTLCs include hashes, and then you need to reveal the hash preimage in order to claim a payment and make the whole payment go through. The problem is that this hash is this hash log is the same along every hop of this route. So if there are 2 hops on this route, which are colluding in some way, maybe belong to the same entity or whatever, they can see that they are on the same path. And maybe they are the payer's first hop and the payee's last hop. So then they know where the payment is going and where it's coming from. So with scriptless scripts, what you can do is that you can, instead of having a hash lock that's the same along this path, you would have just a point, and you can change this point along every hop. So that way you wouldn't really know if if you are on the same path from payer to payee. So this has some privacy benefits.
Okay, and how would you change that point? Would it be deterministic, or does the sender do that, or how exactly would that changing work?
Which changing?
Of the point that is the quote unquote point.
Yeah, so it is. I haven't looked into this for a while, how exactly this works, but it doesn't matter that much. You just need some random number. You multiply it with the generator of the group, so you get a new point, and then you add it up. Now, if it must be constructed in a way that every hop, every intermediate hop, if they get revealed some secret or some secret to a point, they need to be able to claim it on the other side, because they have a hash lock with, or now it's not really a hash anymore. Some people still call it a hash, but you still have this lock. Someone claims the payment from you. Now you need to be able to claim it from the other party, like in the direction of the payer. And so you basically, you just add up points, and every intermediate node knows a part of this point.
Okay. Yes. Okay, that will work. But why is that scriptless script?
I think I forgot that part. So the way this works right now is that there's really a script with a hash, and then later you can claim it with a pre-image, and this script it's part of the transaction that you update, the commitment transaction in Lightning right now. So the way this would change is that you don't have a script really anymore. You just have this signature. So right now, if you do a Lightning channel, you have you create a multisig contract, right? This is visible on chain right now because we use check multisig and not MuSig or something like this. What you can additionally do is that if this output would be spent by anyone, for example, during a channel close or something like this, then an additional secret would be required or released in order to do this. So this additional secret is exactly the same as the hash lock when we do the payment forwards. So what this means is that this lock logic, that we need this hash, we can just encode in the signature itself. We don't need an additional script to do this. And because this is all based on the elliptic curve math, we can just add these secrets to each other, which we cannot do with hashes, right? We cannot add a SHA hash to another SHA hash and then expect that that you can also add the pre-images, and then with the added pre-images you would get the same SHA hash as both hashes added together, right? This doesn't work. But with these elliptic curve computations, this actually works.
Okay, yeah. Um, so, but is that useful, or is scriptless script now, is that useful just for the routing of Lightning payments, or can it be used in other ways as well?
It can be used in, so I mean, it's basically a more specific case, but atomic swaps. Like right now, atomic swaps or coin swaps, as they are always discussed, they have, you see the pre-image on chain. You see the hash and the pre-image, so you know this is some kind of atomic swap. So scriptless script would solve that. You would only see that this would be, it would look like a normal payment because all the logic is just encoded in the signature, but you can still do the same thing. So for example, atomic swap, so Lightning Labs came out with their loop project, which allows you to make a Lightning payment and you receive a Bitcoin on-chain transaction in return. But the on-chain transaction contains the hash. So everyone can see that this kind of stuff happened. And I mean, it's wasteful in terms of block space, but also it's not really fungible.
Yeah. Yeah. Wow, and that is awesome. So when we have Schnorr, like you just see signatures, but you have no clue what it is. Could be a single signature, it could be an aggregated signature from like a MuSig or something. It could be such a scriptless script. And that is the case for all the transactions. So even a single signature increases in its anonymity set drastically because it could be anything.
Yep.
That's insane.
I mean, you can't encode all the logic that Bitcoin script can do in a scriptless script, right? You can just do simple things like requiring an additional secret. But this additional secret can be many things. So I've given a talk last year at Building on Bitcoin about how this could be actually a blind signature over another coin. So what this allows you to do is that, let's say you are a service provider, you do atomic swaps, right? You do an atomic swap with Alice, with Bob, like similar to Lightning Labs loop. Let's say you receive a Lightning payment, you give them Bitcoin on-chain coins. Now, the problem is that you know that you can associate the Lightning payment with a Bitcoin payment, right? You know that they belong together. They are the same person. You got a Bitcoin address from them, right? Before they send you the Lightning payment. So what you can do with scriptless scripts is that you can say, okay, so actually you have many coins and Alice and Bob, they can claim one of them with a blind signature from you, but you don't know who it was that claimed this coin. So you can't see this association anymore. So this is just an example of other things that you can do with scriptless scripts. But I think the idea is that in the cooperative case, if in smart contracts, there most often is some cooperative case where the participants, they agree what the outcome is. It's also cheapest for them, right? Because they don't have to do any complicated stuff, and also it doesn't have to land on the chain. So they can just say, okay, we all agree what the outcome is. Now we create a transaction to settle this contract. So there's always this cooperative case, and this is a multisig. Okay. So most of the time we don't really need anything more complicated, and that means that most of the time this doesn't even need to land on chain. And the idea behind concepts like Taproot is exactly that you have this one case which is the most likely case, everyone agrees on the outcome is, but if this is not the case, then any participant can show a script that the participants agree to. This is the smart contract, and fulfill the conditions of this script. Let's say, okay, you can, for example, spend this coin after 1,000 blocks with this particular secret, instead of having everyone agree on spending it. And with Taproot, this additional condition doesn't even need to be doesn't even need to end up on chain if the cooperative case is actually the one that is used by the participants.
Yeah. I was about to bring up Taproot. Great that you did that, because I did a reading of Greg Maxwell's mailing list post about that, both Taproot and Graftroot. And so the question here would be then, or well, Alice, Bob, and Charlie, all of them, like before they fund that UTXO, they first, of course, provide the aggregated public key, right, for the regular case where everyone agrees. And then they also create, let's say, 50 different scripts with all different cases that they might think that they potentially, or well, of course they commit to that they potentially might want to use in the future. And do I understand it correctly that they then build a Merkle tree of hashes, though, of all these scripts to a Merkle root? And then on chain, you commit to the aggregated public key as well as the Merkle root that commits to all the 50 scripts.
Almost. So you create you put the aggregated key in the output that includes all the participants. But this is a special public key. So all the participants, they can work together to spend this coin, right? But this public key was made in a way such that you can later show, this public key actually committed to a Merkle root. So you don't have to specify the Merkle root in addition. You just have the public key, and later you can show, this public key actually committed to some Merkle root. And then you can show the Merkle path, do the proof that the specific script is included, you show the script, and then you satisfy the script, and this is the other way how you can spend this coin.
Okay, and again, that is fucking awesome, because now we have one additional thing that could be hidden behind a single public key, right? Such, wow, okay. So, but how exactly does that commitment work, and how can it be hidden in the public key?
How exactly does that work? No, the question is, do you want to know the equation or not? Okay, so what you do is, all the participants, they create their public key together. They aggregate a key. This is their public key, but this is not the one that is going into the blockchain. So what they do is, to this public key, they add, let's say, x times g. So x times the base, the generator of the group, and x is the hash of the original public key and the Merkle root, or whatever they want to commit to. So that's basically it. The equation is relatively simple if you write it down.
So basically, so they aggregate the public key. So Alice, Bob, and Charlie have their individual private public keys. They aggregate the public key to one single public key. Then they build up all the scripts and the Merkle root of that. They hash the aggregated public key and the hash, or the Merkle root hash, and that hash then is combined with the generator point to again generate a public key.
Yes, exactly. And so then there are two ways to spend this. The key path and the script path. The key path is just you spend we're using the public key that's already there. And for the script path, you need to show that this commitment actually exists. So you need to show the original public key plus the Merkle root, the thing you committed to. And then everyone can check, okay, yes, they committed to this additional data.
Okay, yes, but then again, in the case where everyone would agree, they can only produce a signature that is for the aggregated public key, right? But on the blockchain, we've committed to the hash of the public key and Merkle root. So wouldn't that mean that even in the cooperative case, we would need to show that the public key for which we have the signature, so the aggregated public key for which we have the signature, together with the hash of the Merkle root, then can or commits to that public key which is in the blockchain. Or
are you asking? I think I didn't quite understand the question. Are you asking if you also have to show that the opening of the commitment if you just want to do the key spend? Was that the question?
yeah. So why is it that in the cooperative case you don't have to show that it is a taproot?
Because everything that's in the output is just a public key, and the participants are able to sign for this public key. So yes, what they have to do, I mean, they created their original public key, and from that plus the data they want to commit to, Merkle root script or whatever, they compute this public key that has the commitment. Now they can sign for both of them. They just need to add to their secret key the hash of the original public key and the data. So they just need to change it in exactly the same way the public key was created, the one that's ending up in the chain.
Yeah, of course, right. So they can, with, as we discussed earlier, with signature, well, to generate the aggregated signature, so to say, that's as we discussed earlier. But then if they just add that aggregated signature with the hash of the Merkle root, it still computes to be valid and proven to the public key which was committed to in the blockchain.
Yes.
Okay, awesome. Okay, cool. And because we have not yet talked about too much difficult shit, where's the difference to Graftroot?
So Graftroot works in the following way. You just have a public key in the output. Everybody can sign for this public. I mean, the participants can spend this key by just producing a signature for this public key that's in the chain. So far that's similar to Taproot, but if there are the additional script conditions, they are not committed to in this public key. So the way this works is that when they create this output, they sign with this public key that is going to be in the chain. They sign the scripts, the additional scripts they want to later be able to spend the coin also with. So if they want to spend the coin with such a script, they just show the script and they show the signature that they've previously created or created later. Doesn't matter when they do it, but I guess in many cases they do it while they set up or before they send coins to this output. So then the consensus can just check, okay, this is a script and there's a signature with this public key or for this public key over the script. So they can also just satisfy this new script now, because this would be essentially the same as making a transaction, sending the coins to the new script. We're just leaving out the transaction, basically.
Yeah, cool. I didn't think about it like that, but that's basically what we're doing, right? Because for adding a new script for Graftroot, you need to have all of the signatures, right? Of the public or of the committed public key.
You need to have a signature for this public key. Yes.
Oh yeah, and you can only compute that signature with collaboration of
Yes.
all parties.
Yes.
Yeah, right. And then they could easily just like spend that UTXO and generate a new output that has then that script included, right? Yeah. Okay. And the cool thing is, because we don't commit to the Merkle root, we don't commit to any scripts, right? So there can be infinite amounts of scripts, and even, well, okay, there can be infinite amounts of scripts in Taproot as well because it's a Merkle tree. But the cool thing is that we can add new scripts after we've done the on-chain transaction. But then the question will be, can we remove a script that we've already committed to? So for example, Alice, Bob, and Charlie have the aggregated public key, and they have one script, for example, that after 1 year, Charlie can spend alone. but now they don't like Charlie anymore, and now, or they don't like that Charlie can spend after 1 year. Can they revoke that script without doing an on-chain transaction?
No, that doesn't work neither in Graftroot nor in Taproot. For that, you need to make a new transaction.
Yeah. Yep, because you cannot unsign what you already have signed, right?
You cannot make it invalid.
Yeah, exactly. Yep. Okay, but then here, in that case, like I would guess one of the bigger hurdles would be that, well, no, not necessarily, just, but you have to back up all the script conditions.
Yes.
And is there a way to do that deterministically? Not really, because scripts are scripts and not keys.
Yeah, I would say that depends on the script, but in general, yes, you need to store them. Like if you have a condition where, let's say it's Alice, Bob, and Charlie, but after 1 year only Alice can spend it, then Alice needs to remember the signatures over the script, because otherwise, if she forgets it, then she cannot claim it later.
But I'd just like to point out that that's the case with any script, because you never commit the script itself in the blockchain, right? You just commit a hash of the script. And if you only have blockchain data, you cannot derive, even for regular pay-to-script hash. So I guess it's pretty much the same, but it's just much more efficient.
Maybe the script sometimes you can recompute, but signatures you can never recompute once you forget them.
Yeah, very true. Okay, I think we covered one or two things. If there's still people watching, holy shit!
I was about to say that. Congratulations if you made it this far.
Watch it again, and if you're back here for the second time, watch it a third time. Maybe then you understand it. Okay, yeah, but is there? Well, of course there is, but is there anything really cool with Schnorr signatures that we have not yet covered?
Nothing in particular comes to my mind. For now, we'll see probably Schnorr signature, work on MuSig, threshold signature. This is what I'm concentrating on. Scriptless scripts. Blind Schnorr signatures would be interesting, and then later we'll see what we can do with aggregated signatures. And all that stuff is happening on GitHub, either in the SecP256K1 repo under the Bitcoin Core organization, or the SecP256K1-ZKP repository in the Elements project.
It takes a long time until you can memorize libsec P256K1 and say it without stumbling over it. Yeah, okay.
Let's not change the curve soon.
No, please, because I just figured out. Oh yeah, okay. No, wait. Talking about curves, yeah. So the problem with elliptical curve digital signatures is that they are quantum breakable, right? And that's why we don't use, or well, we don't commit to public keys, but we commit to hashes of public keys, because SHA-256 is quantum resistant. So how about Schnorr? Is Schnorr quantum breakable?
So yes, just because Schnorr relies on the discrete logarithm problem, and with a quantum computer you can compute the discrete logarithm faster, at least in terms of complexity, than with a classic computer. But I would say it's quite a stretch to say that we have the hash or that we hash public keys in outputs, because previously was just with RIPE-MD, it was just like smaller, just 80 bits. And another thing is that, so Schnorr is breakable. I mean, at some point, it's definitely possible that we need to move to a post-quantum secure signature scheme, but Schnorr definitely isn't. And also, hashing public keys doesn't help that much, because there's so much address reuse already happening. There are so many coins on like very old outputs which are just like paid to pub key, and also you're kind of only thinking about the scenario where it would take the quantum computer long enough to for your transaction to confirm before it can actually compute the secret key, because you're revealing the public key at some point, right, when you spend it, so someone could raise you a quantum computer. So this is really not a very good protection. If we want protection, then we need a post-quantum signature scheme. There's currently a contest, a NIST contest for standardizing that, but it's quite early for that, so there isn't really a candidate, but there are also better schemes already developed in the meantime, which aren't really in the competition. So we're very, very early with these kind of schemes, and also like quite a few of them, they're just very big. So it's really, and slow, and like much slower. So it's really questionable if a system, a cryptocurrency, can work with these signature schemes.
Oh, okay, so please, all malicious adversaries, just leave the quantum computer research off and just do something else. Do something productive. Come on. Okay, maybe one thing that is very interesting, especially for Bitcoin, we have segregated witness, right? And we have a versioning field of segregated witness, so we can upgrade the signature mechanism a bit easier. So the question would be, how can we get Schnorr now into the protocol? Like especially with these with the versioning field.
Yes, because this would just be then ideally just a new SegWit version. So all the back 32 implementations would just work, addresses would work. So even if you so because there's no new address scheme, you could create or you could give someone an address for SegWit version 1, and even if they don't understand it, they can send to it.
Yeah, perfect, right? Because we still have the issue between wrapped SegWit, which starts with a 3, and native SegWit, which is BC1Q, and it's still a bit non-trivial to change from page to script hash, or to send, or it's, if you can send to page to script hash, then it's not then you not necessarily can send to native SegWit. But then if you can send to native SegWit version 1, which is BC1Q, then you could easily send to SegWit version 2. Well, no, actually, we started with SegWit version 0. Okay.
Yeah. Yeah. I have nothing to add. This was correct.
Yes. Okay, and soft fork, right? And
so it's too late. I don't want to get into the politics of how to do a soft fork. I don't I don't know how to do it correctly, but just thinking that probably this time it shouldn't be as controversial, because this hasn't anything to do with the block size, and also many people concerned about the block size. They left this project, including miners. So I expect it to be a lot more uncontroversial this time. But still, we want to I think have that update as safe as possible and not have any network disruptions. So it will probably take a while and longer than we all expect after there is a concrete proposal, until this will be actually active on the network. But in the meantime, we can build the software to support it. So.
Yep. So you heard it here first. It's official. 2 weeks. But yeah, dude, thank you for coming on here. I think we did it. It was like it's the definitive show on Schnorr. We're done. We don't need anything else. Everything was covered.
Yeah, let's see if the cryptographic assumptions hold up in 2 weeks.
Yes. Okay. So I guess any last words? Where can the people find you?
You can find me on Twitter at Nickler, N1CKLER, and otherwise check out the repositories I mentioned earlier.
Yeah, and then just on a complete different side note, his brother, Konstantin Nick, is working on some awesome gaming Lightning stuff. So definitely check out Donner Lab and check out all the games that they're doing and weekly live streams and stuff. And yeah, cool stuff coming there as well, because we have like damn smart minds like Jonas here working on, or somewhat working on Lightning games, right? And then thinking on that. So cool things coming with in-game databases that are no blockchains. So yeah, I guess stay tuned. Again, thank you very much for watching, because like congrats. Like, that was a good job, really. And I will have to rewatch that episode a couple times in order to really like somehow get that in there. But yeah, Jonas, thank you very much. Not just for coming here on the show, but actually for contributing and coming up with that crazy stuff, and making sure it's implemented.
It's not really my ideas. There are many contributors to this project.
Yeah, very true. Okay, peers, stay tuned. Check out the repost and try to understand this, accumulate as much as you can, and then apply it and teach others, and make sure that we understand the power of Schnorr, so that we realize that it really is a great upgrade to Bitcoin with awesome stuff coming. And hopefully we can get it in 2 weeks. So thank you very much, and see you on the next show. Bye-bye.